Final part of chapter 6 that we're going to get into is there is another way that we can actually figure out how much energy is being emitted from an electron when it goes from the excited state down to the ground state, or how much energy is being absorbed from an electron when it goes from a ground state up to an excited state. And the way that we can use it is we can find the energy. We can use this formula right here. E is equal to negative h, which stands for Planck's constant, times c, speed of light, times RH. Now, RH is this thing called the Rydberg constant. Okay, so here are Planck's constant, speed of light, Rydberg's constant. Now, when we multiply all three of these numbers together, negative h times c times r of h, we come up with negative 2.18 times 10 negative 18th joules. And with the Rydberg equation, another thing that we can find is we can use it to solve for the wavelength. So if we take the inverse of the wavelength is equal to the Rydberg constant times 1 over n of 1 squared minus 1 over n of 2. N of 2 squared. Now, these n's represent the energy levels that the electron is going to be at. You know, if it's going to be going from the excited state down to the ground state, or going from the ground state up to the excited state. Now, if we know that what the two energy levels that the electron is jumping to, we can find the energy by this. Change in energy is equal to our final energy minus initial energy. Kind of like finding the delta H, or change in anything, change in temperature. We take negative H times C times R of H times 1 over our final energy level squared minus 1 over our initial energy level squared. So let's kind of look at an example of using this or these formulas. So first one, how much energy is emitted when an electron moves from the 5th energy level to the 2nd energy level? All right, so we're going to be using this formula right here. All right, so delta E is equal to negative 2.18 times 10 to the negative 18th joules times. Now, 1 over our final energy level in this situation is going to be the 2nd energy level. So 1 over 2 squared minus 1 over, and our initial energy level is the 5th energy level, 5 squared. Negative 2.18 times 10 to the negative 18th joules over 1/4 minus 1/25. All right, so let's kind of put that into our calculator. 1/4 minus 1/25. I'm coming up with 0.21. So negative 2.18 times 10 to the negative 18th times 0.21. Now I'm coming up with negative 4.58 times 10 to the negative 19th joules. All right. So, since we are having energy being emitted, that is telling us that our energy output should be negative, because when we're giving something off, we should be getting a negative number with it. If we were absorbing it, it should be a positive number. All right, now, next part. What is the wavelength? So we're going to try to use the Rydberg equation right here. So 1 over lambda is equal to RH. Now the Rydberg constant is 1.096776 times 10 to the 7th per meters times. Now, 1 over N1 squared. So our first energy level is the 5th energy level, so 1/25 minus 1/4 So let's kind of put this in our calculator. 1.096776 times 10 to the 7th times 1/25 minus 1/4. I'm coming up with negative 230,322.9.6 per meter. Okay, now with this, we can't really have a negative wavelength, so what we're going to kind of do is negate that negative and just think of it as a positive. And that is equal to the inverse of our wavelength. So our wavelength is going to equal to 230,229.6 per meter, and we're going to take that to the inverse. So 230,229.6, inverse of that. Now it comes out to be 4.34 times 10 to the negative 7 meters. Okay, now this actually does fall into the visible spectrum. This is equal to 434 nanometers. Now, where does this fall at? This is going to be somewhere in the blue range. Probably a little bit more indigo than blue, but right around that area. Alright, so this should help you with the last assignment for this chapter. If you have any questions, please let me know, and I will talk to you later. Thanks for watching.